We live in a very complicated 3D, multi-body, imperfect world. We'll talk about this highly idealized orbital mechanics framework that we've learned as electrical engineers trying to be satellite communications engineers. Where does it break down? You know, it's interesting that these simple Keplerian laws capture 99.9% of the behavior of the orbits. And the rest of the deviations are important to understand, and you do need to understand, you know, how you're going to correct those, how you're going to change those. But those usually don't impact the communication system in any significant way, right? We're going to be doing link analysis on satellites, so we need to know where the satellites are, because we need to know how much physical distance do we need to overcome for path loss. What angle is the signal going out to the atmosphere in order to figure out where it's going to wind up. Small disturbances in orbits, as electrical engineers, we view that as somebody else's problem. So I said my aerospace engineer was so agreeable. Thank you, thank you. That's somebody else's problem. But you know, we should still be aware of what those problems are. How is it going to impact? Because everything in a satellite system impacts one another. That's the beauty about a satellite. It's a heavily constrained design problem. So you think, oh, I'm an electrical engineer. I don't need to know about aberrations. And then it turns out that the station-keeping fuel that you need is going to limit your total spacecraft lifetime, because you're going to need a certain amount of station-keeping fuel to overcome these degradations and aberrations in your orbit. And that's going to determine how long that your solar panels have to last and how much power they have to be providing at the end of their lifetime to drive your electrical system, which may be operating off of something that's spec'd similarly. So I often liken satellite system design to hammering out the lumps on a carpet, right? You think you knock down one lump over here and two more pop up over there in places that you weren't expecting. You know, your power constraints or your communications design. Or you say, oh my goodness, I now have to have 30% more station keeping fuel because this orbit needs more correction than I was expecting, which means my antenna can be 2 kilograms, has to be 2 kilograms less, which means I just lost 2 dB of gain, which means I no longer can modulate this way. And I mean, it's this kind of endless dialogue and trying to optimize the best spacecraft for a particular utilization. And if you do it right, you save your company millions of dollars. So it's important to understand all of these things. Now, where do these disturbances from our pristine two-body problem come from? Well, one of the disturbances is from a third body. And so what are the other bodies in the solar system? Let's rank it from most influential to least influential. What's the thing for Earth orbit satellites that's going to disturb the orbit the most? The moon, of course. It's not the biggest object in the solar system, but it's by far the closest. So the moon, which is 385,000 kilometers from Earth, radius centroid to centroid. What's the next thing? What's the next body in the solar system that's going to influence? Mars? Not quite, no. The sun. The sun. The sun is 150,000 kilometers. Oh, excuse me, 150 million kilometers. Much farther than the moon, but of course much, much more massive. And so that's why it comes in as a close number 2. A close second to the moon. What it lacks in distance, it overcomes in just sheer mass. What's the third thing in the universe, or in the solar system, and the universe, that influences and tugs beautiful, perfect circular and elliptical orbits out of whack? the third thing. Not Mars. Mars is chintzy. It's tiny. What's the next biggest thing in the solar system? Jupiter. And then everything else is kind of in the noise. Usually inconsequential enough where you can ignore it. These are the three big ones in this order for Earth-based satellites. If you start doing deep space missions, it's usually these two things. And depending on where you are in the solar system, they probably swap order of importance. Jupiter is almost, it's not as massive as the sun and it's farther away, but it's almost like its own star. People who study planetary and solar system formation suggest that Jupiter is a would-be star. A lot of stars are binary in nature. In other words, the solar systems of other places are 2 or 3 stars, and we have a single star system, which is not unheard of, but quite often there's another object that turns into a star. And Jupiter just didn't quite make it in our solar system. Didn't quite make it. Okay. Now, this is a source of perturbation for Earth-based satellites, other bodies. There's another source of perturbation, and that is actually the Earth itself. Earth irregularities. There are 2 types of irregularities about the Earth itself that influences satellite orbits. One is the shape of the Earth. The Earth is actually not a perfect sphere. It is what scientists call an oblate spheroid. And that is a fancy word for a pear. Now, it doesn't look like that from space because the disturbances are minor. Like if you just visually look at it from space at a distance, it looks like a sphere. But it's not perfect. It's actually a little bit bigger at the bottom than it is at the top, just slightly. And you would think that that wouldn't make a difference. But if you put a satellite up there for 10 years and you let these errors accumulate day after day after day, you'll actually notice a difference. The fact that it's an oblate spheroid instead of a perfect sphere. Yes? The south, yeah, the southern hemisphere. A little bit more mass down there than it is in the northern hemisphere. Strange as that may be to contemplate, but it's as a percentage of the mass of the Earth, it's not that significant. But even what is it? If the Earth is 6 times 10 to the 24th kilograms, a few hundred trillion kilograms here or there doesn't make much of a difference in absolute sense, but it will actually distort the gravitational pull slightly with errors that will build up over time. So Earth irregularities. And the other irregularity is something called Masscons. Masscons are regions on the Earth that have different densities. So, for example, let's take a look at the polar view of the Earth. So this is the North Pole. We're looking down at the North Pole. The Earth is spinning this way. But in absolute space, if we ignore the rotation of the Earth, and this is something that is really only important for geostationary Earth orbit satellites, the Masscons. Why? Because those are, they need to maintain exact synchronization with the rotation of the Earth, and they need to have their same alignment with the latitude of the Earth that they started on. And over time, even slight changes, remember these things are moving at thousands of kilometers per second, right? And so if you impart even a slight error, like a half a meter per second, builds into your velocity, over time, that satellite will drift out of its designed longitude and place in the sky. And you'll lose the whole reason why you launched a geostationary Earth orbit satellite to begin with. And so there are, because you're phase locked in the Earth, you know, if you were at a lower Earth orbit satellite, this wouldn't be a big deal for a lot of reasons. First of all, you're always moving, so you're going to have to deal with some tracking anyway, right? Secondly, you're moving around and around the Earth, and whatever irregularities are on the Earth will kind of cancel each other out over time. Not true for the geostationary Earth orbit satellite, because you see the same part of the Earth all the time. So if there's an irregularity, a higher density region on one part of the surface of the Earth than the other, over time, that irregularity will build error up into your orbit. And so it turns out that there are actually two stable points, regions of high density Masscons that attract a geostationary Earth orbit satellite, and then two unstable points. Let me just write where they are. The unstable points are at 162 degrees longitude and 348 degrees. These are unstable points. And then 75 degrees and 252 degrees. These are stable points. And of course, I've drawn this in terms of longitudes. So 360 degrees or 0 degrees, this would be Greenwich, England, roughly. And so over here you'd have North America. Here's North America. Here's like Central Asia, India, the Pacific Ocean, kind of Europe over here. Europe and the Pacific Ocean, very repulsive. North America, Central Asia, attractive, right? I'm just kidding. But that's where the stable and the unstable points are. If you have a geostationary Earth orbit satellite here, over time, it will slowly, without any correction, start to drift over to this stable point and try to settle in. If it's over here, it moves this way. If it's over here, it moves this way. It'll probably oscillate a few times before it gets there. Likewise, if it's over here, everything will start to approach that stable point over there. And if left to their own devices, over the course of many centuries, you would develop these two giant trash stars over the Earth, where all the dead satellites would accumulate. But obviously, we don't see that. So as part of an international agreement, if you launch a geostationary Earth orbit satellite, before the satellite dies, you need to make sure there's enough station-keeping fuel to launch it into something called a graveyard orbit. And it turns out you only need to go about, 200 kilometers beyond geostationary Earth orbit. There's no drag up there, so you're going to stay in that orbit in perpetuity. And that piece of space junk will have just enough motion slower than the surface of the Earth, so that all the Masscons will integrate out and it won't fall into those stable points. So if you launch a geostationary Earth orbit, you must make sure there's enough station-keeping fuel to put it in that graveyard orbit. Any questions about that so far? Okay. Now, a couple other things to keep in mind when we talk about these extra bodies that influence the tug and pull of satellites in orbit. I said earlier that we had a really good question earlier. Well, are all the things in the solar system lined up on a plane? Like, do the planets all operate on the same plane. And of course they do, kind of, but there are some disturbances. So let me sketch out two systems to show you kind of what the angular disturbances are. They're not going to be to scale, but they're just for reference. So let's say this is the Earth, and this is the rotational axis. Not to be confused with the magnetic axis, which is slightly off. But this is the geographic North Pole, and this is the geographic South Pole. And so 90 degrees to that would be the equatorial plane. I've drawn it as a line. It's a plane that comes out of the board and is perpendicular to that rotational axis. Now, a geostationary Earth orbit satellite, we said, had to be on that plane to be geostationary. You can launch satellites at different angles and different planes, and that plane is called the plane of inclination. So when we talk about inclination, we're measuring the angle of an orbital plane from the equatorial plane. 0 degrees would be equatorial. You can go all the way up to 90. That puts you on the poles. And you can even go past 90. If you've gone past 90, we call that orbit retrograde. Because effectively what you're doing is now rotating against the rotation of the Earth. Those are actually more expensive orbits to launch into, because not only, usually you launch everything going with the rotation of the Earth, because you get a little bit of a boost of kinetic energy. Because you're starting out on the Earth and you're rotating in that direction already, it makes sense to kind of launch it in that direction. Otherwise you have to overcome that kinetic energy and then add that kinetic energy back and then launch it into enough, give it enough energy to launch into an orbit. And so for the most part, everything is, most things are in a inclination launch of less than 90 degrees. There are some applications, we'll learn about a couple of them, where you want to launch in a retrograde orbit and have things go against the surface of the Earth, or the rotation of the Earth. So anyway, this is inclination. The moon, the natural satellite of the Earth, it is at an inclination of 5 degrees. This is why we don't get solar eclipses that often, because usually this isn't even lined up with the solar orbital plane. And so then if you go down and look at the Earth-Sun system, so of course the sun actually has an axis of rotation. And it's roughly lined up with the plane of the solar system, but the Earth is actually 7.3 degrees inclined from the sun in its orbits. And then the Earth itself, of course, has a tilt of 23 degrees. Its axis of rotation is actually 23 degrees off from its orbital plane with the sun. And of course, the moon is going to be plus or minus 5, depending on where it is in the system from that. So it's going to kind of wobble around. But only when things kind of line up perfectly do you get things like lunar eclipses and solar eclipses, which is why they don't happen very often. Not every month, every period of the moon. So these are the basic irregularities that affect our orbits or influence our orbital designs around the Earth. Now, I like to kind of conclude this section by talking about a concept called orbital forcing. it's kind of a nice way to tie everything together geometrically, all the things that are going on in a complicated three-dimensional orbit. And it also turns out this is a kind of an interesting topic because it influences long-term climate change, which is a big research topic nowadays. So kind of shows you not just the man-made, but also some of the natural things that influence climate over time. And so these all fall under the topic of orbital forcing that I'm going to talk about. We use a lot of these concepts. These are actually irregularities in the orbit of the Earth about the sun that causes some things that influence the climate of the planet. And I've highlighted 4 things just to show you. They're very similar to things that orbit around the Earth or a satellite that orbits around any irregular object. Now, orbital forcing, many of these perturbances are due to the presence of Jupiter. So if we're talking about an Earth-Sun system, the sun is the biggest thing in the universe, and that's usually the culprit for disturbing other orbits. But if you're orbiting up around the sun, Jupiter is the next biggest culprit, right? And so the presence of that heavy extra body introduces some irregularities into elliptical orbits that disturb the climates. And in fact, because these are quasi-periodic, there are certain climates in the long-term cycle of Earth. They're called Milankovitch cycles. This is a researcher that tabulated these phenomenon historically. And you tend to, when these different cycles tend to add constructively in a particular direction, you get very cold or very warm periods on the Earth. They're actually very good for predicting things like interglacial periods, times when the glaciers are receding or advancing long term. These are usually operating on the order of thousands or tens of thousands of years. So orbital forcing. There are 3 types of orbital forcing mechanisms. Eccentricity variations in the orbit of the Earth. Precession variations. Obliquity variations. And inclination variations. So as a test in 3-dimensional conceptualization, let's talk about each of these individually, and maybe you guys can guess, how do they influence the climate of the Earth? Eccentricity variations. The Earth Earth's orbit about the sun over many, many cycles, thousands of cycles of years, will wobble between 0.005 and 0.058. So it will go to almost perfectly circular. And because of the presence of Jupiter, this third body, and some other disturbances in the universe, in the solar system, and possibly the universe, there will be some tugging, and it may stretch all the way to 0.058, which doesn't sound like that much, but it's still, millions and millions of meters of accumulated distance. Now you think, let's sketch this out for a second. Okay, the sun goes on one of the foci. I'm going to exaggerate the eccentricity to make a point here. Here's the other foci. The Earth is going to be on this elliptical path. Sometimes it's going to be perfectly circular, and other times it's going to be a little bit more eccentric. But the semi-major axis will be roughly the same. Remember, we're not really adding a lot of energy to the Earth. We're just kind of wobbling its eccentricity, stretching it a little in one direction, tautening it up in another. It'll still take roughly 1 year to get around the sun. We'll be at the same semi-major axis. So if we're at the same average distance, would we expect any change in climate? It's a little brain teaser. The answer is actually yes. And why? Why would that be? Think Kepler's second law, equal areas in equal times. Why would a more eccentric orbit change climate? That's right, that's right. The cold weather occurs on this half of the orbit, right, when you're slightly farther away. Instead of saying hot or cold, we can use a fancy term, insolation. insolation, the amount of sunlight that gets into the planet, insolation. Not insulation, the pink stuff you put in the attic. This is the low insolation. And actually, I should probably draw it more like this if I want to equalize the semi-major axis. This might even be shorter. This would be a region of high insolation. Well, you think, well, I got high insolation, I got low insolation. The amount of average insolation, if I average over the path, should be the same. But remember, we're not taking into account time. Kepler's second law says you will speed through this section of your orbit much faster, faster, depending on how eccentric you are, compared to this section. So they may spatially average, but they do not temporally average out. Your planet gets less insolation at this eccentricity than it does at this eccentricity. And it's enough to make a difference, especially when it builds up over multiple years. So it's interesting. You probably never thought about that. The Earth her orbit is not circular about the sun. And what's more, it changes. It wobbles a little bit. Now, how often does it wobble? Well, this occurs in a fairly regular cycle. So if you think it's going to change next year, have no fear. The major cycle is 413,000 years. And there are some minor cycles in between. Yes?
So this process could result in potentially a warmer, quicker summer and a longer, colder winter.
That's right. That's right. And we have to be careful about using winter and summer because it's going to be summer here in the northern hemisphere, but it's going to be winter. We're really net insolation throughout the year is lower. Average insolation over time is slightly lower. But I know what you mean. Yeah, that's the way to think about it. Interesting. Okay. And as you can see right now, our current eccentricity, we're actually a little bit closer to this right now. I have recorded into my notes that last year we were at 0.012, so I'm guessing we are probably at that same eccentricity this year. Almost circular. Colder times ahead. Maybe, I don't know. Not anytime soon. Now, the second orbital forcing element, precession. So let's see. I got the sun. Here's the orbital plane coming out of the board that the Earth makes with the sun. Here in the northern hemisphere, when our rotational axis points away, we get summer. And on the other side of the orbit, we get, this side we get summer. This side we get winter. The south gets summer. And the south gets winter on this side. And for the most part, we maintain this because, generally speaking, when you have a rotating object, the angular momentum is conserved in a particular direction, and you stay oriented like a gyroscope over time in your orbit. However, anybody that's played with a top on a table knows that for short periods of time, that's true. But over time, that axis will actually precess. And the Earth is no different. We actually have precession on the Earth. And what that means is that over many, many times, this will eventually flip over many years. The actual cycle for this happening is 26,000 years. So right now, perihelion coincides with a northern hemisphere winter. And aphelion corresponds with a southern hemisphere winter. So based on that, who do you think experiences the most extreme seasonal swings? The north or the south? Well, the south, right? Because the south is the farthest away from the sun during its winter, and the north is actually the closest during its winter. So you expect those to be different, and the south is going to be closest when it's summertime. And generally, we've observed that. In the southern hemisphere, the seasons are slightly more varied than they are in the northern hemisphere. Now, of course, at the current time, the planet is not particularly eccentric in its orbit. So these are two phenomena that can reinforce one another. You don't see much of a change when E is 0.005, but you may see a more significant change when E is at its maximum of 0.058. Now the question is, does this affect insolation of the planet? Well, the north experiences milder seasonal changes now, and the south experiences more significant changes later, and vice versa. So it's just putting the shoe on the other foot, right? However, it does have a significant effect on climate. Why? What's different between the north and the south hemisphere on the Earth? What'd you say? Yeah, the land mass. There tends to be a lot, thanks to Asia, there's a lot more land mass up in the northern hemisphere. More trees, less algae, and you get these seasonal swings can influence the biomass significantly. But you don't have to worry. Those of us in the northern hemisphere can relax in our extremely mild winters and our extremely temperate summers for the next 13,000 years. Okay. Number 3, obliquity. Obliquity. This is also related to the Earth's rotational axis. And this is kind of a peculiar phenomenon. But the Earth's axis, you've always learned it to be 23 degrees roughly from the sun, from the solar equator, or the plane, the orbital plane that the Earth makes with the sun, let's call it. That actually varies over time as well, to a maximum of 24.5 degrees to a minimum of 21.5 degrees. So we're kind of somewhere in the middle. This change happens on a 41,000-year cycle. The current obliquity is 23.44 degrees. So almost smack dab in the middle, maybe a little closer to the end, but certainly not the most extreme that the planet can get. And this is a problem too. First of all, it doesn't affect net insolation, but the higher the obliquity, the more extreme summer and winter become, the harder it is to grow things. That also influences the biomass significantly on the planet. And who knows what that does. And there's one final change, and that I don't believe we have a good estimate for the cycle that this happens, but we know that it happens and that it will have an influence. The sun, this is inclination of the Earth orbit. The sun has sort of a median plane over which all of the planets revolve around it. And the Earth has a slight amount of inclination with respect to that plane. What do we say, like 7%, 7 degrees roughly? So it's a little bit off. And it'll go around and around in this fashion. But it also wobbles. It will tilt up and down and up and down over tens of thousands of years at least. Now, why would that change anything? Well, it has to do something with a question. We have to go back to a question that somebody brought up earlier, which was really good. And that is, does everything lie on a plane in the solar system? And the short answer is yes, most things do, because you form these accretion disks that turn into planets and all. However, not everything belongs, not all the mass belongs to a planet. There's a lot of debris, most of it just dust size, that exists all along here. And so, for example, we notice that twice a year, on opposite ends of the year, when we pass through the accretion disk, the median plane where there is more stuff, we see a slight increase in meteor activity. There's more dust and particles and little rocks and fragments that fall into the Earth. And so scientists speculate that when the plane lines up with this mass, that will result in slightly less insolation because it just gets a little dusty. You don't notice it from Earth. It's probably not observable on a day-to-day basis, but it will slightly lower insolation, which will build up over time and change the climate until the Earth comes out of that inclination of 0. So I always think this is interesting because it kind of teaches you to think in 3 dimensions, and it reinforces a lot of the orbital concepts and irregularities that we learn in the class. And there's always a lot of talk about climate change. There's a very good, healthy discussion to be had about how do man-made things influence the climate? What should we do to change or alter behavior? The one thing you must never do, though, is say something that one of my colleagues said one time when I was out to lunch with them. He says, it's clear that we are violating some sort of equilibrium in the planet with our activities. It's like, there's never been an equilibrium in the planet. It's been chaos since the beginning. Deal with it. So, any questions about irregularities or orbital forcing? You'll be happy to know that the next ice age isn't until 50,000 years. So we're safe. We're safe. Yeah?
A slingshot around, or I guess getting into orbit, like around Jupiter.
Mm-hmm.
Does its moons play a significant role? Or is
that's a good question. That's a good question. The short answer, the question to repeat back in case you didn't hear it on the video or in the back, was when you're inserting yourself or slingshotting with Jupiter, do you have to consider the mass of the moons around Jupiter in your calculation? And the short answer is probably yes. It's not that hard to do, so I'm sure that the solvers model those anyway. It probably doesn't make that much difference, though, because Jupiter does have a few very large moons, but still, as a fraction of the total mass of the planetary system, it's much smaller than the percentage mass of, say, the Earth's moon and the Earth. The Earth is actually very unique as a planet because it's almost considered a dual planetary system because its satellite is one of the biggest satellites in the solar system. And it's almost to the point where you can't even, you have to model the centroid of the two, as so many hundreds of kilometers away from the center of the Earth. So it really is almost like a dual planetary system that orbits around itself as it progresses around the sun. Now, when you're dealing with the Earth, and you can approximate the satellites around the Earth because you tend to be a good bit farther from the moon, and it's not nearly as massive as the Earth. In that scenario, geostationary Earth orbit and less, you don't usually have to worry about it other than to correct your orbit every once in a while. When you get out to the moon orbit, if you want to orbit something that's really far out in higher Earth orbit, then you start getting into some weird orbital mechanics. There are these stable points, for example, called Lagrangian points around the moon, where if you insert a spacecraft in there, it'll just kind of hover in moon synchronous orbit. It'll just kind of in between the Earth and the moon, or you can spiral it around the moon in a semi-stable orbit as it tracks around the Earth. There's a lot of really interesting orbital mechanics that you can get into, but obviously a very specialized application. Okay, how are we doing on time? Oh, 1 minute left. Any other questions before we leave? Yes?
So you said that everything on the solar system is pretty much in sling.
Roughly, yes.
So I'm assuming the asteroid belt is too.
That's right.
There's an asteroid belt between Jupiter and Mars. So how does the orbital mechanics that really want to play into that? Do you navigate through it or right above?
How do you go through the asteroid belt? Well, it's true that there's a lot of junk in the asteroid belt, but as far as navigating through it, you pretty much play the odds. The density of the belt is extremely low. It's a 1 in a huge number shot of actually running into something. It's not like Star Wars where they have to oh my goodness, or like any other space. That's always much more dramatic to portray asteroids in that fashion. But the sad matter is it's just slightly more dense than all the other junk out there. There probably aren't giant space worms living on there either. But that's just a guess. Don't quote me on that.